then I ended up doing it this weird way, where
Alright, guys.
now it enters this, but it's skipping this one.
So we have a quiz today. After the lecture, it's going to be 2 problems on the quiz. I'll give you about 15 minutes to work on it.
So is it over the SSD as well?
No, SSD will be quiz 3 next week, Tuesday.
Oh, okay. So it's just the floating point.
Yeah, just floating point and the parity bit generator. It's pretty simple.
Cool.
Yeah. So next week, Tuesday, will be another quiz on 7-segment display. So today we'll run through some really satisfying experiments. It's laying the groundwork for another very good experiment in the next following weeks. For example, the VGA. So we'll be able to load the data of the image and throw it to a monitor and display over there. It's really interesting to see. So I added, compared to last year, I added 1 more task, but it's not making this too much worse because it's only 4 tasks. So this week will be a lot better than last week. Okay. So the simulations for the flip-flops are pretty simple. So task 1 is a no-brainer, just simply repeating the simulations. The code is already provided on the websites, 1 through 3. I think they are just SR flip-flops or D flip-flops or T flip-flops. So 20 points for that. And the second one will be a debunk circuit. This is the new one just added to this tutorial. I'm gonna go through that, probably spend 20 minutes today to talk about that, because I found out it's really interesting to know and useful to use for the course project in the very last maybe 2 weeks for this term, for the Yoshi's Nightmare, that game. You have to use a joystick to control the movement of the character in a game, and you have to engage that push button to the game as well. So when you push it, you can definitely use a debunk circuit in Verilog. But I'm just trying to let you guys try hardware debunks, so it can reduce the amount of code you have to put into your either Verilog, or in the future, if you use the microcontroller, it could be the C, right? The C code. You don't have to use the debunks to occupy, to take the space in the loop. And a couple of other simulations. I think this one, the test benches for these tasks are not given, so you have to write the test bench by yourself. And the last one is really fun to do. It's loading of memory. It's a new technique that we are going to learn in this tutorial. So to know this one will be very beneficial for the soft core experiments, maybe in 3 weeks from now. Think about that. When you guys are putting a soft core into the FPGA, it's a very simple basic storyboard. You're actually putting a CPU in it. And combining with the memory over there, you can put all your assembly code in the ROM, the read-only memory. So you're creating a little microcontroller similar to whatever you guys are learning this term in the microcontroller class. So you're creating Arduino, not instead of using Arduino. It's not as complicated as Arduino, but it's adding more assembly code to your semester. But it's easier, definitely easier. It's a very simple 8-bit CPU. Okay. So before we get into the first few sections, let's review the lectures first. It's been a while, I think, for you guys. So most of you haven't taken my digital circuit, right? You haven't taken that class. For SR latch, you can use either NOR gates or NAND gates. If you use NAND gates, bubble here, it's feeding back to the 2 inputs. So if I'm defining that this is output Q and this is Q bar, Q naught, okay? I always ask this question, which is R, which is S? So SR means it's a setting and resetting. The setting and resetting, right? So it's a setting and resetting latch. Setting and resetting latch. And all these fundamentals are super important when you are doing an interview with a digital design job. very likely this will be on the interview exam. Okay, so if this is SR latch, which pin is R, which pin is S? So which pin is setting it, which one is resetting it? So when we're talking about that, it's like when you give a 1, so for either R or S, you give a 1, you turn it on, okay? You give a 1, you turn it on. So when I'm asking that question means, if I give a 1 here, a 0 here, am I setting it or resetting it?
Reset?
So usually when saying it's setting or resetting, you are talking about Q, right? So are setting Q or resetting Q. So if you give a 0, you don't even, so you want to start from here because of NAND gate, right? So you're definitely getting a 1 here. 1 is being fed back to this port. So you get a 1, 1, and eventually you're getting a 0. So it's resetting Q. Okay? If you turn on this pin on the top, it's resetting Q. That means this pin on the top is R, right? So if you give this is the 1, this is a 0. So you never, for the NAND gate SR latch, the normal operation code for the inputs are either 1, 0, 0, 1. That's by definition, okay? If you give a 0, 0, what's going to happen? If you give a 0, 0, is that going to burn the circuit?
No.
No, it's just unused. We never use 0, 0, 0 for the NAND gate latch, SR latch. But it's not going to blow it up. It's it's just giving you 1, 1 for Q and Q bar. But since we want to define this one as a Q bar, which is the inverse of Q, so we never put a 0, 0 as the input for the NAND gate SR latch. It's just unused. So what about 1, 1? So 0, 0 is unused, right? So this is unused. 1, 1 will be a memory because if you put a 1, 1 here, it's not affecting anything. Whatever this signal was is being fed back to here. You are still getting the same result. It's not being changed. So it's called a memory status. So 1, 1 will be memory. Okay, 0, 0 is unused. And these are the normal operation. It could be either 1, 0 or 0, 1. So 0, 1 will be setting it because S is being turned on. You got a 1 for S. So reset is off. You give a 0 to R, which means it's not resetting, but the 1, you give a 1 to S, it's setting. So in that case, Q will be 1. So when you're setting the latch, Q becomes 1. So that's the SR latch using a NAND gate. So what about NOR gate? Could you form a SR latch using a NOR gate? I'm still defining this as a Q as a Q bar. So which is S, which is R? Let's try it, okay? Let's put in some numbers in there. If we have a 0, 1, what's going to happen? So NOR gate, right? We want to start from here because 1 will give you a definitive answer for output for the NOR gate. So you are getting what here? 0 here. Okay, so 0 will be fed back to here. 0, 0 becomes 1. All right. So 1 being fed back here, 1, 1, 0. So stable. Okay. 1, 0, 0, 1. Stable. So it's going to stay there. So which is R, which is S? Is Q being set or reset right now? Set. So which is S? Okay. So that's R, right? Since you turn on S, and now it's being set. So that's the NOR gate SR latch. And in the real world, okay, if you have a switch, okay, a circuit like this. What's the name of this resistor? Pull down resistor. Why?
When there's no current, it shows ground.
No current shows to ground. So there's, if I don't have this switch connected to this terminal, what's the voltage here? 0 volts, because there's no current, right? No current, no voltage drop. 0 volts, 0 volts. being put down to ground. So if I have a circuit like this, what's the voltage here? 5 volts. It's being put up to 5 volts, okay? So at the moment that I switch this one to this terminal, what's going to happen to this terminal? So before I switch it here, the terminal's voltage was what? So before I switch it here, wait, did I? If I switch it there, it's still going to be 0. So it's probably want to connect this pin here, right? Start switching this one here. Disconnect this point, but this is still connecting here. Yeah, I'm confusing you guys. Sorry. Let's redraw it. So it's going to be a 5 volts terminal. Here's a switch. Okay, like this.
And that's a ground on the other side of the 10 resistor, right?
Yeah. So if I switch this guy here, okay. So it was 0, right? So the voltage here was 0. So when I switch this one to the like a wiper or something, switch the wiper to this terminal, because the mechanical component is going to bounce back and forth. It won't give you a steady 5 volts ideal case. You know what I mean? Because the mechanical component, right? It's going to vibrate back and forth. So that's why it's going to bounce back and forth for a while and then stabilize at 5 volts. All right. So that's why you want to debounce it. Is this a switch or push button? Ask this question first. Is this a switch or push button? Since we have used different components in the lab, it could be we have switches, we have push buttons. We have used this one in a lot of projects. Is this a switch or push button? It's a switch. So what a switch looks like? It has 3 terminals, right? 1, 2, 3 pins. And have a little knob on the top. You can switch it. It's either connecting these 2 or connecting the bottom 2 pins. Okay, if you think about the component we have in the lab, it's either switching to these 2, connecting these 2, or connecting these 2, right? You're switching up or switching down. It's going to implement this circuit here, right? It's either connecting these 2 or these 2. A very, very quick question. In this circuit, which one is the middle pin? Which one is the middle pin here?
5 volts.
Down the top. Good. You're getting that. It's very simple, but cool. All right. Can we, since it's bouncing back and forth, how do we debounce it? So you can use a NOR gate here. A NOR gate, what's that called? SR latch. And you short this one to ground, use a resistor, is pull it down to ground. Okay. So in that case, here's 5 volts. And it was connected to here, right? So if we do this, I think Ian asked this question before, right? So if we use SR latch, how do we build a debounce circuit? That's how you do it. So why is this debouncing Q? Like what we talk about here, okay, for this circuit, for R and S, okay, it has 0, 1, 1, 0, 1, 1, 0, 0, okay? Let's fill up the truth table here. If I get in 0, 1, what's going to happen to Q? Yeah, it's setting, right? Because S is 1, so we turn on S. So this one, the second entry here will turn on reset. You're getting 0 here. 1, 1 is what? Is 1, 1 unused or 1, 1 the memory?
It would be the memory because it's NOR keys. Oh. No.
So 1, 1, let's try it, okay? Let's try it. So if I have,
I think it doesn't work, right?
It would just automatically put 0.
yeah, for example, we have 1, 0 here at the very beginning, okay? As a previous state, 1, 0 like this, okay? If we give a 0, 0, what's gonna happen? 0, 0 to the NOR gate SR latch. So this was 1, 0, so 0 will be fed back here and 1 will be fed back here. So 1, 0 NOR is giving you what? So these two is giving you what? 0. And 0 being fed back here is giving you what? 1, right? Is that stable? It's not flipping anything, right? It's stable. If we have 0, 1 as the initial state, so 0, 1. Okay, so 0 will be fed back here, and 1 will fed back here. Okay, we still keep the input to be 0, 0. What's going to happen to the output? 1, 0 NOR will be what? 0, right? 0, 0 NOR will be what? 1. Is that stable? Are we changing 0 and 1 so that 0, 1 is the initial state? Are we changing it? No, so it's always 0, 1. So which means when we enter the 0, 0 input, it's not going to change the state. So previously the input could be, if we're having a 1, 0, for example, okay, what was the previous input? It's giving you 1, 0 here. What's the previous input? Why? Because it's setting it, right? So from 0, 0, 1 to 0, 0, are we changing the output? No, so it's a memory state. So 0, 0 will be memory. But 1, 1 will be unused. Okay? So now we look at this circuit again. So after finish this one, I'm gonna ask one of you guys to draw the NAND gate version for me, see how that works. This is a debunk circuit using SR latch, but NOR gate version. Okay. Now you guys let me know why this guy is debouncing Q. When it's getting to 0 and 0.
When? Oh, it's the set and reset for 0.
So here's a switch, right? So imagine because this schematic doesn't show the physical layout of the circuit, right? It's just schematic. So if you have a physical switch instead of this one, you know, on the physical PCB board. So I have 3 terminals. So which is which? Which one is which one? The middle pin is what? 5 volt. This pin is? Yeah. Okay. So there is a you switch it to the top or bottom, right?
Or when it's in the middle, it's 0, 0, so it's just looking at memory.
Yeah. When that happens,
when it's in that.
when you move it, right? Your hand is slow when you move it, but you think you can switch it really, really fast, but compared to the clock frequency of the computer, it's really slow. So whenever you switch it from here to the bottom, it vibrates a lot. So there will be a lot of noise being generated. In that case, so your computer is reading really fast, running all the loops really fast. So it is able to read every single data point in the noise. So giving you a really, really noisy output. However, if you have this debunk circuit, whenever it's flying or moving in the middle. It's not connected to anywhere, it's just in the middle, right? So these two are being put down to 0. This is forming a memory state for the SR latch. So this one will memorize the previous state. It's not changing to the next one. But if you think about this connection, are you getting 1, 1 at the same time? Is that possible? No. It's either this one will be shorted to 5 volts or this one being shorted to 5 volts. Just giving you either 1, 0, 0, 1 for the inputs. Does that make sense? This is going to debounce your switch. So we're going to look at the debounce circuit of the push button later, but anyone can volunteer to draw the non-gate version of the debounce for the switch.
Just do the same, but instead of pull down, you have pull up.
Yeah. What else?
You lost.
5
volts switch to 0.
Yeah. Let's see if that works.
I think it's gonna be RS, not SR.
It's always RS. It's always RS. For either NAND gate or NOR gate, it's always RS. Remember that. Is there any difference in between the pull up resistor and pull down resistor? No. What are these? 10K? Why don't you use a 10 ohms? Yeah, because 10, so at 5 volts over 10 ohms is what? 0.5 amps, like 500 milliamps. It's pretty smart design. So what about here? Grounded, right? What's the voltage for ground? 0 volts, right? Okay, I got a switch. It was here, and you'll switch it here. 1, 1 for NAND gate based SR latch is a memory state for it, right? No problem, because 1, 1 is not changing anything to the NAND gate. But compared to the NOR gate, you are giving a 0, 0 as a memory. So that's the only difference. So if you are only having NAND gates available in the lab, you want to use pull up resistor to 5 volts and short the switch to ground. So you have 3 pins on the switch. The middle pin should be grounded, right? Yeah. Make sense? Super practical circuit. What about push button? A lot of times you hate switches because you can easily break the little knob on the top. So what about the push button? It's easier, just push, right? Hurts your finger if you have a little print on your finger.
Get nicer buttons.
Yeah. How do debounce push button though? Could you use the same circuit to debounce the push button?
You just force both of them to the end of the. Wait, no, that wouldn't work.
What's the difference between the switch and push button? So the switch, you are either shorting the top two or bottom two, right? That's a switch. So push button is the one we use in the lab. It has 4 terminals, and I think these two are shorted, these two are shorted, right? When you push it, you short the bottom to the top. So it's like this, right? 4 pins, right? 4 pins. It's either a wire or a broken circuit, or open circuit. So I found a design online. You know, it's called a Schmidt trigger. It's a IC that you can use. You can find out from the electronics lab. But anyway, before we go into there, so can we, if you are building a debounce circuit on the breadboard using one of these techniques for one of the projects maybe happening towards the end of the semester, are they synthesized NAND gates, or they are, or IC chips that I can find in the lab? How would you build it on the breadboard?
On the breadboard, they have to be discrete components.
Yeah, it has to be discrete components, right? So you have to grab a little IC block which has an AND gate or NAND gate in there, and resistors as well. You are not able to do it on the IPGA because you have analog devices like resistors. Okay, but for the Schmidt trigger, it's the same, very similar. And there's a component called inverting. Oh, it's called inverting Schmidt trigger. So the symbol looks like this. It's just two terminals. So what this one does is, it has a hysteresis. Hysteresis. Can I spell it? Hysteresis. RESIS. So when the voltage of the input goes up, it switches to 0 at a certain voltage, and when it goes down, so this is a positive going threshold voltage. It's called a V plus. It's called positive going threshold. And when it's going back, when the input voltage goes down, it triggers it at a different threshold voltage from the hysteresis. So that's V minus. That's a negative going threshold. I have two different threshold voltages. Could you think about any applications for this type of behavior? I mean, just in general, it's not just for this type of IC. Have you seen anything behave somewhere in a similar way in your real life? So if I draw a diagram, it's a really interesting thing to know, very practical. If there's something like this, okay, and the temperature here is 200 Celsius, like in the oven, okay. Whenever the voltage, whenever the temperature passes this temperature, for example, the heater of the oven will be turned on, and whenever it's lower than that temperature, no, when it's lower, you turn on the heater. When it's higher, you turn off the oven, right? So it's going to be switch on and off all the time. It's similar to the HVAC in the house, right? The thermostat. You don't want it just at one point at the threshold voltage, at the threshold temperature, because it's always on and off. It's always switching on and off. It's really annoying. So really, desirable design is that you have a hysteresis for this design. For example, you have like the set point is still 200 Celsius degree for the oven. Maybe you want to set up the threshold temperature for the higher level, the higher end to be 202 Celsius, and the lower one to be, whenever it goes down, it turn it on at 198 Celsius. So it's not always on and off. Being switched on and off frequently, right? It has a little area buffering region for the temperature to go up and down. Very similar concept. For this circuit, to debounce the push button, what you can do is, so this is the behavior of the Schmidt trigger, okay? It's an IC block you can find in the lab. And to debounce the push button, we can do this. It's a 5 volts, it's a pull up resistor, and that's ground. Here's a button, okay? And that's a 1K resistor. This is a cap. Could be 10 microfarads. and then the inverting Schmidt trigger. Okay. Could you predict the outputs at nodes 1, 2, 3? That's exactly what the task 2 is asking you guys to do. Okay. I should add something to it, but just let you guys know, when you build a circuit on the breadboard, you have to probe here, here, and here when you push the push button, and to show the diagrams on the oscilloscope and put a figure in your report. So could you predict the output from here, here, and here? So the voltage here was what? You know, you are pushing it down at a moment. Before you push it, it was what? High, right? If you push it, what's going to happen? It's going to do this, right? It's going to bounce back and forth because the mechanical wiper, you push it, you think it's being pushed down, but actually it's bouncing back and forth for really high frequency for a few microseconds, which is not undesirable. This is really undesirable because your digital circuit can possibly read any of the points in here and give you a uncertain voltage. What about number 2? Yes, low pass filter. Yeah. You know that filter really well.
Used it once or twice.
2 years of pain.
Hope I know that one.
Yeah. Oh, where's Noah? 2 other people are gone. Yeah.
Well, while we're at it.
Yeah, just let you guys know. I mean, who maybe you are not really familiar with that. You haven't been in my classes. But the low pass filter is just an RC filter like this. It's really simple. You don't have to. We are not doing the calculation here yet. But you just need to know it's going to filter out all the noises and smooth it out, right? So eventually, what's going to happen here is instead of having a really noisy output, you're having a delayed ramp, so it's getting delayed because these noises are trying to charging and discharging the cap, but since you have a pretty big, very big cap, it's not able to, and the resistor limiting the current, it's not able to give you a really smooth output. Instead to getting a really sharp edge, it's having a slower, delayed ramp or falling edge like this. All right. So what about number 3? Look at the behavior of the Schmidt trigger again. So the inverting Schmidt trigger, which means it's not just giving you the hysteresis, but also delaying the voltage output. Okay, so this filtered signal will be fed into the input of the Schmidt trigger. Okay, so there will be a slower falling edge. So it was high, okay, it was high, and it's falling to 0 with a time delay. Where you want to start with on this diagram?
The end where it's flat.
And where it's flat.
Oh,
I use an op amp with infinite open gain.
this one.
No, so this is high to low, right? This is high to low, okay?
So it would come in and then it would.
From here, right? So that's the input. That's in, that's out, right? Yeah, it's high to low. What's going to happen? You have to follow this arrow, right? So it's not using a inverter, like something like an inverter is like switching at 2.5 volts is not. It has to fall to some point. It's pretty close. I don't know what the voltage is, probably 0.1 volts or something. And then switch to high. So why this helps getting rid of these things? Or probably this is already gone after the filter, okay? So whenever it's falling down, it only switches somewhere around here, okay? It's giving you a rising edge, which is sharper rising edge. Why is getting you a sharper rising edge, you think? Why is that?
On the other side of the inverter.
That's the Schmidt trigger.
Yeah.
Oh,
Please. That's what I'm talking about for 15 minutes already.
What's it? It's a non. Wait,
it's
this is an inverting Schmidt trigger, which is just an op amp.
Yeah, so it's going to the other side of to the left hand side of the curve. It's using this one, right?
Oh, are we using the op amp in it like a comparator?
Where's the op amp? Where's the op amp?
In the Schmidt trigger, I have a schematic.
Okay.
Understand what is going on there.
Yeah.
So is it using the op amp like comparator? So when it reaches that closer to the low, then it's
not a
flipping?
comparator configuration, isn't it?
Let's get back to the input first, so you know what we are doing here. Okay. First, what's the goal of this circuit? To debounce the push button, right? Okay. So you push it, you got a noisy zero here, and then you filter that out, you got a slower folding edge, and now we want to get rid of the slow folding edge. So we use this Schmidt trigger. And why this one will give you a sharper rising edge here? Because when the voltage is going down, it won't do anything until here. So whenever it arrives or reaches this negative threshold voltage, but it's not negative voltage at all, it's like 0 point something volts, it's going to exactly trigger it. If you look at the diagram, it's going to trigger the output to be 1, right? That's why you're getting a sharp rising edge. Because all this part is not doing anything. That makes sense? So what about a very slow rising edge? Same thing. So this part is not going to do anything, but until this point, it reaches a positive threshold. It's going to give you a sharp folding edge, right? So you can nicely debounce the push button, but you got an inverse signal instead of exactly what you have over here, which is fine. It's just a switch. Does that make sense? This could be very useful for the project, FPGA project later in the semester. So we're going to do this exactly the same circuit in the lab as part of the tutorial, the tasks. I think that's task 2.
We're doing that in lab today.
Yeah, no, anytime this week. It's just homework, yeah. So build this circuit on the breadboard and probe 1, 2, 3, and show it on the oscilloscope. Okay, make sense? So the chip, I will probably grab the chip from the lab, from the electronics lab. It is a Schmidt trigger. Has 4. Oh no, not 4. 8 probably. Yeah, 8. Is that 8? 7? Why did they choose an odd number? That doesn't matter. Just pick up one of them, right? But don't forget to ground it and power it up. Just power, ground, and you have multiple channels. It's pretty simple. Okay. So now we have learned a lot of debouncing techniques for all different applications or platforms. Could you tell me what they are? So what is this one used for? What is this one used for? Could you let me know? When you want to use this? When it's a button, right? And you already have a super long code and having nested loops or interrupts and everything, and you don't want to put one more debouncing circuit in there to add more complexity to the circuit, right? So this can be used for FPGA, it can be used for Arduino system, which you need a push button in there. And if you have to use a switch for the circuit, you can choose either one of them. Okay, either the non-gate version or NOR gate version. Okay, and beyond that, we're going to learn a debounce Verilog module later this semester. You can put it in the IPGA board, so and synthesize it as a debounce circuit, integrate it into the chip. In C, right, you can write a C code to debounce as well. I think there's a chance that Dr. Whittyworth will teach it in the semester to debounce it using. It's pretty easy, right? Just put a delay in there, I think, in assembly. So you can definitely debounce something in assembly with microcontrollers, or you can debounce. So just find out the debounce C code for Arduinos. It could be really easy to do, just maybe no more than 10 lines of C code. All right. Okay. Now the first few sections of the tutorial become super simple, since you know what this one does. What is this called? SR latch. So for the NAND SR latch, what's the memory state input? Which kind of input we'll put into the memory state? Something don't kill the NAND gates, NOR gates, right? If you give a 1, you don't have choices. It's going to be 0, 0. So it has to be 0, 0 as the inputs to keep in the memory state. So you can see 0, 0 is giving you a previous kill. It's actually a memory state. 1, 1 will be unused. But could you use it at all? Is it going to blow up the circuit? No. It's just giving you an unused input. Why? Because 1, 1 will give you a 0, 0, but we really want this pin to be Q bar, but it's not giving you a Q bar here. So it's not useful at all. That's why we use it. It's giving you Q and Q bar. That's how we use it. We need a Q and Q bar in there. If you give a 1, 1, it's all zeros, both zeros. It's not working for our purpose, right? So you can definitely describe it in Verilog in multiple ways. But what's going to be synthesized in the IPGA will be totally different. It will be way more complicated than this. This is what you can build on the breadboard, but actually the Verilog code probably is creating like more than 10 gates just to do the same behavior like what the SR latch does on the breadboard. But it's okay. There are integrated circuits. You don't really care. But it does the job. Right, just describe the behavior. So it's a sensitivity list. You have S or R. Okay, when S changes, you update Q and Q naught. If S is 1, you set it. See, Q is 1. If R is 1, you reset it. Does that make sense? Okay. That's a concatenation. You got 2 bits over here, Q and Q naught, right? So the 1, 0 assigned to Q naught, 2 bits binary number. And this is another. Wait, what is this? That's a test bench and the module combined together, right? It's a simulation, pretty straightforward. And this is called the SR flip-flop. You add one more stage in front of it. It's forming a flip-flop. So what's the difference between the latch and flip-flop? So flip-flop is getting clocked. So you are controlling the output by a clock. It's a combinational logic circuit. If you don't control it, whenever this one changes, you get Q updated. It's not controlled. Sometimes you want to control it, like a latch on the door. You open the door, the data will be sent out. Otherwise, they stay at the previous state. So when you want to control it, you have to add another stage in front of it. They are both AND gates. So if I'm asking you guys, if clock 0, if the clock pin 0, what's going to happen to Q and Q naught? If Q is 0, if clock is 0, yeah, it's a memory. If clock is 1, what's going to happen?
RMS get passed.
Mm-hmm.
So
It's just a normal latch. So what's happening here is you have to consider clock as another pin in the sensitivity list. So it has to be clock and S to be 1 at the same time in order to pass whatever S and R, right, to Q and Q naught. Then you how to design a clock in there in your Verilog code. How to design the clock? You could definitely invert flip a pin, the clock signal line, right? In a loop. But here I think it's just the 4 cycles, and clock is always 1. Because only when clock is 1, the AND gates are able to pass R and S to the latch. Otherwise, it's disabled. Right? But are you covering the case that when clock is 0? I think it's being covered over here. If clock 0 is not doing anything, right? Because when clock end the signal, it's just giving a 0, so it's not entering any of the entries. So it's definitely being covered. That logic, that possibility of input is being covered, actually. D flip-flop is a data flip-flop, which is the 1 input pin, but the clock is still the same configuration, but the data pin for the I and R, instead of giving R and S, you just invert one of the inputs and fit it into another input of the AND gate. So basically just the 1 input as a data. So when D is 1, Q is what?
Fair.
Yeah. So which means Q is 1, right? Cool. Why is that? Because D is at this S, right? It's S pin. Cool. Good catch. What about over there? Is that clear? When D is 1, S is 1, so Q is set, right? It is recorded. Oh, these are easy part. So sometimes you want a level trigger D flip-flop. This is definitely level triggered, and you want an edge triggered as well. So at one more stage, it will be edge triggered. I don't think I have a task. Oh, there is one. So you are just it's pretty simple. You know, that's why a lot of digital design engineers in Qualcomm and Intel or any of the companies, they don't know the digital circuits at all. I've seen the people are getting $150,000 a year. They don't even know how the transistor works. Because if you look at Verilog, do you really need to understand what's going on for the circuit?
No, it's great.
See, pulse edge clock, then do something, right? Negative edge clock, do something. That's it. You just describe it. So it's like a 5-year-old kid, right? You don't even need to understand this. It's just request. I want to do this. I want to do this, and just do it. Ask the synthesis tool to do it. These are JK flip-flops. So one thing to remember is it's always passing J. I think, do you know what JK means? Yeah. It's a Jack Kelby who invented integrated circuit in the 1960s or 1970s and won the Nobel Prize for that. I think he was one of the founding, member in TI. I think TL Intel, maybe TI, Texas Instrument. So JK flip-flop is always passing J to Q. Just remember that. So J, if J is 1, Q is 1. If J is 0, Q is 0. It's very simple. Don't complicate it. Very simple. But if you short J and K and short it to one logic 1, then you'll form a T flip-flop. So T flip-flop is when you connect J and K to 1, whenever the clock arrives, it's toggling the output. So it's being very useful for a counter or for clock divider. Registers. One quick question here. So this is a shift register, and what is the type? What type of shift register it is for this guy? These are data. These are cues, output, input, output, input on the top and output at the bottom. Serial in, parallel out, serial in, serial out, parallel in, parallel out, parallel in, serial out. Which one? Yeah, parallel in, parallel out. You got 4 bits, parallel in and parallel out. You just need a clock to trigger the flip-flops and send all the 4 bits at the same time to the output. Could you see that? So D is D flip-flop, so D is being sent to Q, and D is being sent to Q. It's just like a latch. When clock arrives, it just sends all the 4 bits to the output at the same time. So it's parallel in, parallel out. It's not like a parallel in and then shift it out, right? That's parallel in, serial out. Or you have a serial pin and parallel out. Okay, you pump each bit in for 4 clock cycles and pump the 4 bits whenever it's ready, pump them out at the same time. That's called serial in, parallel out. But this is a parallel in, parallel out. Memory, skip it, not really using it. ROM, very useful, read-only memory, and we're going to program a ROM in FPGA. Is a fun part of this tutorial. So you're writing a module called ROM. It's a little bit different from the other Verilog scripts we have used. So look at it. So the ROM is a Verilog code, okay? It's a digital circuit, but the data itself is from a different file. It's called memory.mem. You create a text editor and code it up in Vim. You can put the data into this memory file. So that's one of the memory files. That's why you have to know how to use them. So when you create these numbers, it's just a copy and paste all these lines, and then replace one of the digits over here. Okay, still very tedious, but these are binary bits being stored in the memory.mem file. And this is something new in Verilog. Okay, $ read the memory file, and it's a binary file. So which means all these bits are binary bits. It's just a 0, 1, 0, 0, 0, like that. Okay, and you read the memory file as the name of the memory file. And that's the name of the module, okay? Here. So read the data into this memory space that you created using this Verilog code. That's a register, 8-bit. Each line is a byte, and you have 260 what? 250 what? Or 260 what lines? 256 lines, right? So that's the depth of the memory. That's the length of each line or each memory cell. It's a byte, and have how many bytes? 256 bytes in there. So that's the memory file. That's how you initiate or declare a 20. It's 8 by 256 memory cell. All right. So the ROM has an enable pin, the chip enable, read enable, the data in as the data out, the address. So whenever the address is an 8-bit address, does that make sense? Why is it an 8-bit address? Why is it an 8-bit address for the memory?
You have to add some other bit string to it, like the physical address or something.
But why 8 bits? Why do you need the 8 bits?
Oh,
Could you-
because it's an 8-bit system, so you have to, wait, no, never mind, never mind.
Could you use 9 bits? Could you use 7 bits address? So what is determining that that length of the address here? So the address is for what? You have a memory bank, right? I have a memory bank. Let me draw it on the paper probably. So the memory bank has,
Is it because there's 256 lines,
mhm.
and so you need 8 bits to,
to enter every address, right? So if you have 7 bits, part of the memory banks are not going to be accessible at all, right? You throw a number in there, but you'll never be able to get them. So can you use 9 bits?
You can.
Yeah, you can use 9 bits. It's just a more availability here, right? For a bigger depth or a deeper depth of the memory bank, but never use some of the numbers over there, 50% of the numbers, right? So you need 8 bits of address to be used for the 256 memory banks or bytes. So that makes sense, right? It's an 8-bit address. So what is this line doing here? So data is the output. Data is a 8-bit output. So 8-bit output is just whatever in the memory. You put an address to the input. See, it's the input, and then it's going to output the certain data in that address or at that address. So this line is going to do the job. So why is this doing the job? What does CE and read in mean? So it's a read enable. So you want to enable the reading of the memory, and C is a chip enable. You want to enable the chip. So basically you turn on the chip, and you enable the reading functionality of the chip. Yeah, if that is on, then what? Yeah. Just output a 0, right? So if you are not turning on the memory, the data output will be all zeros, 8 zeros. So you know the default data over there, which is 0. If you don't have the chip enabled, it's going to output a 0 to data. So what is this doing? Mem and address. Just taking in the argument of the address, right, into this mem and enter one of the lines in the memory, right? Okay? So this is a memory chip. It's called a ROM. It's a read-only memory, since you are not writing anything to it, just reading. So this is where you load the data. You load the data. So where's the data? Data's here. How to create the data? Just copy and paste. Use the vim commands and flip some of the numbers over here. You don't have to create a 256 lines. I don't think you have to. How to replace a digit? R, right? Just press R, you can replace it.
A lot of R.
A lot of R's. Is there a, so I don't put a file here. Any other way you can create this? You probably can do it using Python, but probably not worth the effort. Yeah.
It would be really easy to do in Python.
Yeah, just create probably 20-something lines. Just never read anything after that line, so it's going to be nothing in there. So this is a test bench of the ROM. This computer battery in this laptop has been how many years? Almost like 6 to 7 years. I got a new computer, new laptop from the college. I haven't transfer all the files to it yet. Okay. So let's take a look at the test bench for the ROM. So definitely in the test bench, you have to include the ROM as a unit. Okay, ROM, U, UUT, UUT1 doesn't matter, just ROM. So connect the address to it, enable it, right? Chip enable data. So what you want to really do in the test bench, since right now I got a memory bank and you want to verify what's in there, right? So what you really want to do for the memory bank, if you don't look at the code, just think about it. You got a memory bank. What you want to do to verify it? So the memory bank's ROM itself is able to read this manually generated data. Okay, you have a memory chip. It's a digital block, has all the combinational logic to select, to output any data in any of the memory entries to the output using the address. Okay, and now you need to design a test bench to look at the data at the output. So what you want to do in the test bench to do it, to verify it. So this guy is available, right? So now I have a ROM. This is called ROM. Oh no, this is a memory bank. This is a memory file. So you have a ROM. The ROM has other circuits to do the data output and as of data, right? And I have address. So these are a bunch of digital circuits in there created by the ROM module. So if you need to create a test bench, what you want to look at for this ROM. So there will be a test bench over here to do something, right? So you want to cycle through all the addresses and then output the data to the output and look at it in the monitor. So I have to create a test bench that is able to cycle through all the addresses to see it. So you can use a for loop in there to do the job, to cycle through all the addresses, right? So that's why you need a for loop over here to increment a 1 each time. If you don't have that many, don't put a 256 there, maybe 20 or something. Okay, this is straightforward. So if you increment the address by 1 each time, and you can expect that your data output will be 1, 2, 3, 4 like that, because that's each line of the memory file, right? Okay. You can change the format of the data from binary to hex. So for example, here, that's what I have in the memory file. These are hex numbers, not English. Are they hex? Yeah, they're hex numbers. Right. So each hex digit here is how many binary bits? 4, right? So what is D in binary? Yeah, it's 13. 8 plus 5, right? So it's 1011. No. No, 1101, right? 1101. Yeah, I've taught this for 5 years. You have to trust me. You know, it's 1101. What is A? 10, right? 1010, right? So what is E? 14. 1110. So these are hex numbers. And because you can imagine that the simulator in Vivado is able to combine all these binary bits and show you a hex number in the monitor, so you can actually have all these English letters, words in there, right? It's combining all the binary bits and giving you these hex numbers. You are reading dad and beef in there. So one more thing you need to know is it doesn't matter which kind of is that called a spacer? What's that called? Spacing? No. Splitter? No. Line separator? Separator, probably, that's the name of it, right? So the separator of different data cells doesn't have to be lines, new lines, it could be a space. So for example, if you align your memory like this, if this is 0 address, this will be 1. Okay, it's from left to right and top to bottom. So you can align the data in a 2D format, but it's for reading from left to right and bottom, top to bottom. So 1, 2, it's like 1, 2, 3, 4, 5, 6, so on and so forth. Does that make sense? So if you align your data like that, you know you're expecting this is 1, this is 2, this is 0, this is 1, 2, 3, all right? Okay, so you can see are incrementing the data by 1 each time, so it's reading from left to right and top to bottom. You can also read 3-bit. Okay, that's easy. There's one more thing that is new in this tutorial. You can definitely create a ROM file, the Verilog module by yourself, but also they have IP cores. I think this is really exciting because this is the first time we are using an IP core in the design EDA tool, which is Vivado. They provide, so it provides a lot of IP cells, especially the memory files, all different kinds of memory IPs. You can create the IP using the wizard here. You know, like following all the steps, it's going to create a memory chip for you. Okay, and just follow all the steps. So you want to load a data file to the memory, and this is the data file that I can download from the website. There's a link at the bottom of the page. And just follow the steps, and have to write a test bench for it by yourself. That's the most challenging part of the tutorial. And I think first run the simulations, do the debouncing with the Schmidt trigger. Make sure that you include the figures and testing results on the oscilloscope. If you don't know how to do it, you know, I can help you during the office hours, Monday, Tuesday, and Wednesday next week. As this is, I think this is due next Thursday, so you always have the time. But I will be in my office during other time frame as well if you need help to work with the oscilloscope. Any questions about this tutorial? If no, we'll do the quiz now. No questions?